Assalamualaikum warahmatullahi taala wabarakatuh and good morning. I'm Dr. Sabah Bau from the Physics Section, Pusat Pengajian Pendidikan Jarak Jauh, University Science Malaysia. This is course JIF 318, Quantum Mechanics. We are in Chapter 3, the Schrödinger Equation. In this Unit 3.3, we'll discuss the operators for energy and momentum. The objective of this lesson basically is you should be able to derive the operator for the energy and the operator for the momentum. Energy and momentum plays an important part in describing a particle in quantum mechanics. Let us start with the derivation for the operator for energy. We start with the general wave equation. Psi equal to B exponent I, and the bracket is the component for the waves, vector K dot vector R minus omega T. Remember that B can be complex number, and of course the exponent there with the small I also contains complex numbers. Taking the derivative with respect to time, remember that we have two variables there, position and time. So if we take the derivative with respect to the time, basically we differentiate psi or the wave function with respect to time t. When we differentiate the exponent, basically we differentiate the exponent values with respect to t, and of course r is silent in the sense that r is supposed to be constant. So when we differentiate the exponent, we have I negative I omega. That's why we have here negative I omega. Please look at the useful mathematics sheets for differentiation for exponents. Okay, so basically when you differentiate whatever is in the exponent with respect to whatever, for example in this case t, you must differentiate it and it should be placed in front of b. Multiplying both sides by IH bar. Why we need to multiply by IH bar? Because finally we want to get the terms E here. In the previous segment, we have defined E as H bar omega. But now we have negative I omega here. In order to eliminate negative I and replace it with H bar, so we multiply the term negative I omega with I H bar. So I multiplied by I basically give you negative 1. That means I multiplied by I squared equal to negative 1. And negative will basically cancel the negative sign here. That's why it is positive here. So when you multiply by this, you have this term H bar omega, which means that we can replace it with energy. Okay. But whenever you multiply the right hand side of the equation with IH bar, you need to multiply the left hand side with IH bar too. Okay, so now that's why we have IH bar on the left hand side. So IH bar multiplied by delta psi divided by delta t equal to H bar omega, then BE whatever it is, that's the general wave equation. Okay, so H bar omega is E, and B, E exponent I and whatever in the bracket is psi, because as the definition up there shows that we can replace this with a psi. So you can see here that your equation now become an operator here multiplied by psi equal to a value here multiplied by psi. So this relationship or this equation is similar to whatever Schrodinger equation we have. That means as a general form, in the general form, the equation should be an operator multiplied by a wave function equal to a number. It can be complex number multiplied by psi. So it is in the same form when we discuss eigenvalues and eigenfunction. So basically, from this relationship, you can see that linear operator multiplied by eigenfunction psi equal to eigenvalue multiplied by eigenfunction psi. So the term on the left hand side before the psi, IH bar delta per delta t is considered as the operator, linear operator for E. That means, in other words, you can say that the operator for E is operator for E. Usually operator we have a cap there equal to IH bar then delta per delta T. So this is the operator for energy. Okay. So from here we can determine the operator for energy. What about operator for momentum? Expanding the dot product, because when we talk about momentum, basically it is with respect to distance, velocity or whatever, because basically momentum P equal to mv. That means mass and multiplied by velocity, and velocity is related to distance. Okay, distance with respect to time is velocity. Expanding the dot product in the general wave equation, the same equation, but now we expand the dot product of K and R. Vector K dot product vector R. Since it is 3 dimension, so vector R is basically represented by x, y, z, and K by kx, ky, and kz. So when you dot product vector K and vector R, this is what you get. I in the bracket kx, x multiplied by x, plus ky multiplied by y, and plus kz multiplied by z. And of course, omega t time, it has no x or y or z component. So since we have 3 components or 3 axes x, y, z, when we differentiate psi with respect to position, then we have 3 partial differentiation like this. That delta psi per delta x, when you differentiate with respect to x, then you differentiate the x component or x coefficient here, ikx. That's why we have ikx here. Again, you have to familiarize yourself with the differentiation of exponents. And when you differentiate with respect to y, you have iky here with z, ikz here. So this is how we differentiate when we have the 3 components x, y, z. Then we must also remember that there is an operator del psi. Sometimes we call it del operator. The name for this triangle, inverted triangle, is nabla. Okay, is defined as x with the head here is the unit vector. That means it is showing direction with respect to x-axis. So del or nabla psi equal to unit vector x delta psi per delta x plus unit vector y delta psi per delta y, and so on and so forth. So we put in the values of our partial differentiation just now with respect to x and so on and so forth. Then we have this relationship, and ikx multiplied by unit vector x and so on and so forth is actually just ik, because all kx x multiplied by unit vector x and so on and so forth is actually vector k. Remember that k is the wave number. Okay, so we have this relationship ik. We are del or nabla psi equal to ik psi. But we want to have or derive the momentum. Remember that momentum we have determined before this, vector momentum p equal to h bar vector k. So in order to have that form from this relationship, we multiply both sides by negative I h bar. Okay, so I multiplied by I squared, that is equal to negative 1 multiplied by the negative sign here, that's why we have positive here, and h bar k is equal to the momentum vector. When you multiply on the right hand side with negative I h bar, you have to multiply the left hand side with negative I h bar too. So we have this relationship I h bar del psi equal to h bar k vector k psi equal to vector p multiplied by psi. So this again, this equation similar to the general Schrodinger equation, where you have an operator multiplied by a wave function must be equal to a value. It can be a vector in this case multiplied by the wave function. The wave function is called eigenfunction. Eigen means a characteristic function for that particular situation, and p is the eigenvalue, and the negative I h bar del or nabla is the operator for momentum. In other words, if you have momentum like this with a small cap, there's momentum operator should be equal to negative I h bar del or nabla. Okay, that's the operator for momentum. So in conclusion, we now have two operators for which psi, or when the wave function is an eigenfunction. This is the operator for energy, excluding psi, and this is the operator for momentum. Okay, thank you very much for your attention.